Welcome to a scientific exploration of how artificial intelligence can optimize cooking by simulating the fundamental physics of heat and moisture transport in food. Cooking is fundamentally a problem of coupled heat and mass transfer, where temperature gradients drive thermal diffusion, while moisture evaporates from surfaces and migrates through porous food matrices. Let us begin by establishing the fundamental physical processes that govern cooking. Consider a piece of meat exposed to high temperature. Heat flows inward via conduction, while moisture evaporates at the surface and diffuses through the protein matrix. The heat equation governs temperature evolution. Here, alpha is thermal diffusivity, typically 1.4 times 10 to the minus 7 square meters per second for meat. Moisture content M evolves via diffusion with coefficient D, minus an evaporation term at boundaries. These coupled equations define the cooking problem. A fundamental question: what actually determines how long we must cook food? Cooking time scales with the square of the characteristic length L. Double the thickness, and cooking time quadruples. This L squared over alpha scaling is fundamental to all diffusion processes. For a 5 centimeter steak, we estimate 18,000 seconds, or about 5 hours, for complete thermal equilibration. Of course, we cook faster by accepting gradients. Now let us examine the 4 critical physical mechanisms in detail. First, thermal conduction. Heat flows from hot to cold regions following Fourier's law. Temperature gradients drive heat flux. The steeper the gradient, the faster energy flows. Meat has thermal conductivity around 0.5 watts per meter Kelvin. Fourier's law: heat flux Q equals negative thermal conductivity, K times the temperature gradient. Second, convection at surfaces. Hot air or water transfers heat to the food boundary. Fluid motion carries thermal energy to the surface. The convection coefficient H depends on fluid velocity and properties, ranging from 10 watts per square meter Kelvin for air to 500 for boiling water. Convective flux equals H times temperature difference between ambient and surface. Third, evaporative cooling. Water molecules escape the surface, carrying latent heat. Each kilogram of water requires 2,260 kilojoules to evaporate. This massive latent heat dominates surface cooling and crust formation. Evaporative heat loss equals mass evaporation rate times latent heat of vaporization. Fourth, protein denaturation. This is the actual cooking transformation at the molecular level. Folded protein chains unfold and aggregate when heated. Myosin denatures at 50 Celsius, actin at 66 Celsius, collagen at 68 Celsius. These temperatures define doneness. Denaturation follows Arrhenius kinetics with activation energy EA. Rate doubles approximately every 10 degrees Celsius. Now we frame the optimization problem that AI must solve. What exactly should our objective function be? This is not trivial. We must balance multiple objectives: maximize tenderness by collagen breakdown, preserve moisture content, develop flavor through Maillard reactions. These often conflict. A weighted objective, function J, combines tenderness, penalizes dryness, and rewards flavor development. The weights encode our preferences. Our control is the temperature profile T of T. We can vary oven temperature, use ramps, sear, then braise, or employ constant low heat. Different strategies: sear high, then low in red, versus constant low temperature in blue. Each produces different internal temperature and moisture profiles. How do we simulate this physics computationally? Let us discretize the problem. We discretize space into a finite element mesh. Each node tracks temperature and moisture. Grid spacing determines accuracy versus computational cost. Finite difference approximation of the heat equation. Temperature at node I and time step n+1 depends on neighboring temperatures at time n. Boundary conditions couple the food to its environment. These determine heat and mass flux at surfaces. Robin boundary conditions mix Neumann flux and Dirichlet value conditions. Heat flux equals H times temperature difference plus radiative and evaporative terms. The complete surface energy balance includes convection, radiation with Stefan Boltzmann, constant sigma, and evaporative cooling. The simulation requires accurate material properties, which vary with temperature and composition. Thermal conductivity increases with temperature, but drops during phase transitions like protein denaturation. Capturing this requires empirical correlations. Specific heat capacity is mass averaged over protein, water, and fat fractions. Water dominates with 4.18 kilojoules per kilogram Kelvin. Let us perform a quick energy calculation. Consider a 300-gram steak from 5 to 60 degrees Celsius. Sensible heat is 58 kilojoules, using an average specific heat of 3,500 joules per kilogram Kelvin. But evaporation of just 20 grams requires an additional 45 kilojoules. So evaporative losses are comparable to sensible heating. This is why surface drying profoundly affects cooking. Now let us examine the crucial process of collagen conversion to gelatin, which determines tenderness. Triple helix collagen fibers unwind into gelatin at temperatures above 60 Celsius. This conversion is time and temperature dependent. First-order kinetics govern collagen breakdown. The rate constant K increases exponentially with temperature according to Arrhenius' law. With activation energy 89 kilojoules per mole, the rate doubles every 6 degrees near 60 Celsius. This explains why sous vide at 56 Celsius for 24 hours works. A fundamental insight: high temperature for short time can equal low temperature for long time if total denaturation matches. This curve shows equivalent cooking times. 65 Celsius for 4 hours equals 70 Celsius for 1 hour in terms of collagen conversion. Moisture transport is more complex than pure diffusion due to capillary forces and protein shrinkage. As proteins denature, they expel water from the matrix. This creates pressure gradients that drive moisture outward, competing with evaporative surface loss. The moisture equation includes a source term, S-squeeze, representing water expelled by protein contraction. This couples moisture to temperature history. Why do we see puddles when meat is overcooked? The physics explains this. Water expulsion rate is proportional to denaturation rate. Rapid heating causes fast protein collapse, squeezing water out faster than it can redistribute. Slow cooking allows moisture redistribution. Fast cooking traps moisture inside until proteins suddenly collapse, then it floods out. The surface presents unique physics. Maillard reactions require temperatures above 140 Celsius and low moisture. A dry crust layer forms where moisture drops below 10% and temperature exceeds 140 Celsius. This thin zone, typically under 1 millimeter, dominates flavor. Maillard rate depends on sugar and amino acid concentrations, with activation energy around 100 kilojoules per mole. Rate explodes above 150 Celsius. High heat searing creates a steep temperature gradient. Surface hits 200 Celsius, while interior stays at 30 Celsius. This gradient is almost 2,000 Kelvin per centimeter, driving massive heat flux inward while developing surface crust. Now we integrate machine learning. The simulation is our physics engine, but AI finds optimal cooking protocols. The workflow: propose a temperature profile, run physics simulation to predict outcomes, evaluate quality metrics, iterate. We frame this as reinforcement learning. The agent controls oven temperature, environment is the food physics, reward is eating quality. The optimal policy pi star maps current state, temperature, and moisture fields to next action, the temperature setting. The RL loop: agent proposes action, simulator computes state evolution, reward signal grades outcome, agent learns from experience. A neural network represents the policy, mapping sensor readings to control decisions. Input layer receives temperature sensors at various depths, hidden layers process spatiotemporal patterns, output suggests next oven temperature setting. The network maps current temperature profile and elapsed time to optimal oven temperature. It learns from thousands of simulated cooking runs. Training requires massive simulation. We generate millions of cooking trajectories with varied protocols. Each bar represents one simulated cooking trial with randomized initial conditions and temperature profiles. Diversity ensures robust learning. What computational cost does this training require? Let us estimate. Total cost is number of trials times steps per trial times spatial nodes times cost per step. For 10,000 trials, 100 times steps, 1,000 nodes, and 1 microsecond per node step. This gives 1,000 seconds, or about 15 minutes on a single CPU. Parallel execution reduces this to seconds. Quite feasible. Pure simulation has model errors. We calibrate using real cooking experiments, then transfer learn to refine the policy. Simulation provides cheap, abundant data. experiments provide ground truth. Combining both via domain adaptation yields accurate models. What do optimal cooking profiles look like? AI discovers non-obvious strategies. AI often finds brief high-temperature sear, then exponential temperature decay to maintain constant core heating rate. This balances crust development and moisture retention. An exponential temperature profile. Time-constant tau controls how fast we transition from searing to gentle cooking. AI rediscovers reverse searing. Low-temperature cook first to desired doneness, then brief high heat for crust. This separates objectives. First stage. Low heat brings core to target. Second stage. Flash sear adds crust without overcooking. Total time often less than conventional methods. Advanced optimization considers spatial variation. Different regions need different thermal histories. For a roast, we might want well-done exterior, medium at mid-radius, and rare at center. This requires precise temperature control and knowledge of heat transfer. And that is how AI optimizes cooking by simulating the fundamental physics of heat and moisture transport in food. Thank you for watching.